I'm Farzana Abazari, former postdoctoral researcher at University of Saskatchewan. In this presentation, we are going to talk about language and platform-independent attribution of heterogeneous code. Code authorship attribution aims to identify a developer of a given code based on unique characteristics of the code. Software forensic and malware analysis are among the top applications of authorship attribution. The traditional attribution methods focus exclusively on the attribution of source code and expect a homogeneous set of files. Traditional research also focused on attribution of binary files, which are compiled in the same architecture. This is not possible in practice. So, main challenges in authorship attribution is that source code is not always available. People used to write code in different languages, and also the attribution is expected to be performed on a mixed set of binary files and codes. So to address these problems, we propose an attribution approach that supports attribution of code irrespective of its format. The earliest studies in this field were limited to an analysis of a single language and consider language-dependent features like abstract syntax tree. Abstract syntax trees can be helpful in representing source code. However, its construction and parsing is language dependent and time consuming, while the amount of generated features is also unscalable. More recently, researchers began analyzing semantic features and become interested in the impact of different compilers, optimization levels, and obfuscation techniques on the accuracy of attribution. However, they showed that attribution of binary code is also challenging. For example, relying on instruction-level features results in significant accuracy degradation, while utilizing features extracted from control flow graphs is sensitive to obfuscation. So, as opposed to existing attribution approaches that focus on either source or binary code, we focus on language and platform and architecture oblivious solution. We propose a simple method for attributing code regardless of its format without any prior knowledge of code specifics. So in this research, we want to know if it is feasible to propose a simple yet effective method for attributing code regardless of its format without any knowledge of code specifics. And we also need to find a set of features that are resistant to compilation process and also persistent across programming languages and platforms. So in the first step of our approach, we represent code regardless of its type as a set of consecutive bytes. This consequency allows us to generate a grayscale image and leverage spatial analysis to deeper textual analysis of the image. And in the last step, the characteristic patterns across all authors' works are explored to drive uniform representation of an author's coding style. So this figure shows the flow of our attribution approach, which starts with representing a code with a grayscale image, filter it to highlight a specific pattern in the image. Then we use a spatial analysis to extract a set of features, and then use some machine learning technique to attribute the features to authors. So in the first step of representation, the input code is converted into a grayscale image. Visualization of binary files have been used in many areas of security like obfuscation tool detection or malware classification. The input code, either in human readable or machine readable, is converted into a grayscale image. These images also contain noisy and rare patterns that are irrelevant for attribution. So to filter this noise and highlight the significant patterns, we use a sliding window to iterate through the matrix and tokenize the input. Later, filtering is done based on the engram frequency within the image, and also the significance is calculated based on the information gain. For each file, we select the top most frequent engrams, which results in a set of engram across all samples. We further use information gain to measure each engram importance for attributing a sample. So we only select those engrams which has a high information and filter the image based on that. Since the extracted image is a numerical representation of byte values, image texture represents the spatial organization of the gray level of the pixels in code samples. We employ two well-known approaches to statistical analysis of the image. The first approach, called heraldic features, which is based on a GLCM matrix and therefore represent the global pattern and feature of the image. We can calculate the energy, contrast, the similarity, correlation, and homogeneity of the pixel in the image. In the second characteristic, we calculate local binary pattern, which conveys local patterns that are extracted directly from the image. This metric measures a local representation of image texture by comparing each pixel with its surrounding neighborhood pixels. Previous studies in source code attribution employed various classification algorithms for attribution. Among them, random forest was one of the most common classifiers that performed very well in comparison with many standard methods. So in the attribution of code, we use 47 features that include heraldic and local binary pattern vectors and image height and image width. To estimate the accuracy of attribution analysis, we use stratified Fulford class validation with random forest classifier that ensures all the developers are presented in all folds. To evaluate our results, we employ a commonly used metric in attribution, indicating the weighted average attribution accuracy. So the critical aspects of this work is the analysis of our approach in the presence of a heterogeneous code format. We thus ventured to collect a mixed code in form of binary source code and code in different stages of compilation across different architectures and compiling configuration. All data sets were prepared to ensure we have at least 5 samples for each format of file per author. So in our validation set, we use Android application market F-Droid, which contains 348 Android projects written by 50 authors, with a varying number of APK ranges from 5 to 22, and also DEX code, which ranges from 5 to 25, and Java source code ranges from 5 to 856. We also collected another dataset from GitHub starting January until October 2020. It contains 475 authors, which all of them has at least code in 2 languages. And we have 378 authors with multiple binary file format. The last data set is Google CodeJam dataset, which is from a competition from 2008 to 2018. This dataset contains 3,000 authors with source code file written in 15 programming languages. Each one has 2 to 5 different languages per author. For our validation study, we attribute APKs to their authors based on bytecode contained in DEX file and original Java source code file. This figure shows that the accuracy for all levels varies between 100 and 82%. The most consistent attribution is achieved with source code, which is 92% for 5 authors and 89% for 50 authors. This is consistent with our expectation, as we know that source code inherently preserves the developer's coding style and serves as a reliable characteristics. So to examine the performance of our approach on multi-language source code dataset, we design a set of experiments to analyze the effect of dataset size and number of languages on the accuracy of attribution. So we randomly select subset of authors from both GitHub and Google CodeJam datasets to explore behavioral of our approach on smaller sets. This figure shows that our approach can obtain attribution accuracy of more than 70% in most cases. As we know that in several studies, it has been noted that experiments with a GitHub dataset is in almost all cases give lower accuracy than Google CodeJam programs. And as we can see here, the total set of GitHub set authors, which is 475 with 25 languages, is attributed with 71% accuracy, while Google CodeJam with 3,000 authors and 15 languages shows 71.8% accuracy. Most of the previous works focused on analysis of files compiled for a single architecture like x86 that makes their binary authorship attribution solution ineffective for analyzing modern malware, which can be designed for various architectures. This figure shows the performance of our approach in attributing binaries which are extracted from GitHub. As we can see, the attribution is reasonably better on compiled binaries like ELF and PE files than those binaries that are in different stages of compilation, like Java classes and compiled Python. And also we can see that overall PE files have the highest accuracy, which is 84% on 50 authors. In this experiment, we investigate the impact of obfuscation techniques on attribution of source code. In our experiment, we use Tigris as an obfuscator tool, which is designed for C language. For this experiment, we randomly select a subset of Google CodeJam datasets consisting 50 authors with 7 samples per author in average. So, as we expected, the attribution accuracy of original code is higher than attribution of those obfuscated code. And also, as we can see, the control obfuscation, in the control obfuscation, the performance drops only by 8.5% compared to the original source code. Visualization transformation, which is one of the advanced control obfuscation, only slightly decrease our approach accuracy by 1.5%. To better assess our proposed approach, we compare the performance of our attribution approach with three techniques called MVFCC, which is a binary code attribution approach, and another language oblivious attribution method proposed by Zafar, and also the Kaliskan approach. To compare with Kaliskan and Zafar approach, we selected subset of Google CodeJam dataset with Java and C++ source code to ensure we have at least 7 samples per author. The result, which is shown in in this table, we can see that our proposed approach achieves higher accuracy in most cases while providing more flexible and broader frameworks for attribution of codes. We cover various formats without prior knowledge of any code. For fair comparison, we also obtain an original dataset employed in approach introduced by Haddad Paju, which is called MVFCC. As we can see, in case of MVFCC, we were able to attribute samples of APT malware group with accuracy of 96%, which is comparable with the result reported in the original study, which is 95%. However, our approach performs better in terms of accuracy and efficiency. This work offers a unified approach for accurate code attribution. We adopt a coding style preserving abstraction scheme, which enables us to accurately attribute code to its corresponding author without any knowledge of code format. This paper's findings have important implication for developing a heterogeneous system that can relate any form of user output to the corresponding author. Thank you all for joining this presentation.
Hi everyone, I'm Song Qige from Institute of Information Engineering, Chinese Academy of Sciences. My presentation today is for a paper accepted for SecureComm 2022. The paper title is Multi-relational Instruction Association Graph for Cross-Architecture Binary Similarity Comparison. This slide lists the main contents of our presentation. Cross-architecture binary similarity comparison aims measuring the functional semantic similarity of binary SNPs compiled from different CPU architectures. It is critical in various security applications, such as vulnerability detection, puncture analysis, and malware lineage. Cross-architecture binary similarity comparison is non-trivial because different architectures have separate instruction sets with different mnemonics, registers, calling conventions, and memory access strategies. The left figure shows the assemble code compiled from the same source code snipped separately on the x86 and ARM architectures, and the generated instruction sequences look completely different. Traditional binary comparison approaches are categorized into two technical routes, static analysis-based and dynamic analysis-based approaches. The former compares the syntactic or statistical features of dissemble instruction sequences, but the gap in instruction sets makes them less effective. Dynamic-based approaches compare the runtime state information or the input-output pairs of binary fragments, but it is challenging to perform scalable analysis on large-scale collections. Considering these disadvantages, researchers have recently focused on learning-based approaches. They generally adopted the following working paradigm. First, generate the initial instruction representations by manual features or external pre-training. Second, exploit deep neural encoders to individually visualize each binary snippet. Third, calculate the similarity score based on the distance matrix. Although showing promising results, these approaches have two main dilemmas. First, they individually encode binaries of different architectures. It will accumulate the semantic gap of different instruction sets, resulting in inaccurate comparison results. Second, pre-trained instruction representations rely on high-quality code corpora under diverse architectures and comparison settings. In this paper, we design a novel approach to alleviate these deficiencies. We first give a formal definition of the problem. The input of our task is a pair of binary snippets compiled on two different architectures, and the output is a semantic similarity score in the range of 0 to 1. 1 represents the input pairs are compiled from the exact same source code, and 0 means their source code implements completely different functions. This figure shows the overall workflow of our approach, including 4 major modules: instruction representation module, instruction sequence encoding module, graph-based instruction association module, and binary similarity comparison module. We will introduce the technical details of each module. This figure is the working process of instruction token visualization. The input binary snippets are discrete byte streams. We first extract their dissemble instruction sequences. Each instruction contains an opcode and a set of operands. We treat each independent opcode or operand token as a basic unit, set up a trainable embedding layer to learn its dense vector with their original semantic information. Then we extract the char-level features to enrich the token representations with lexical information. We set up a char embedding layer and one-dimensional convolutional layer to extract the local spatial features of the char sequences within the instruction tokens. The final representation of an token is the concatenation of token embedding vector and char vector. Note that our instruction visualization process is implemented entirely through learnable parameters without relying on any external pre-trained embeddings. In the instruction sequence encoding module, we deploy BLSTM network, separately encoding forward and backward contextual information of the instruction token sequences. After the encoding layers, the binary snippets are represented as the sequences of token hidden vectors. They will be used for subsequent instruction association and refinement process. In the graph-based instruction association module, our goal is to model dependencies of instructions from multiple perspectives and refine the quality of token representations, bridge the gap in the semantical spaces of cross-architecture instruction sets. We design 6 types of edges to represent the relationships between instruction token nodes, including edges of mono-architecture token pairs and edges of cross-architecture token pairs. For mono-architecture tokens, we define opcode operate operand edge as type E0 and operands co-occurrence edge as type E1. Take the MOV R0 R4 instruction as an example. We associate opcode token MOV with operand tokens R0 and R4 by the edges of type E0. Meanwhile, tokens R0 and R4 are associated with the E1 edge, denoting that they co-occurrence within the same dissemble instruction. These 2 types of edges will establish context-based dependencies of the mono-architecture token sequences, improving the semantic representations of opcodes and operands without resorting to external instruction pre-training. For cross-architecture instruction tokens, we define opcodes prefix match edge as type E2. We connect two cross-architecture opcos with the same n-prefix characters. It is meaningful for identifying instructions implementing similar functions. For example, the SUB, SUBSD, SUBPD, SUBSS of x86 architecture and SUBS of ARM architecture will perform similar operations, and they all contain the SUB prefix. Then we define cross-architecture operands value match each as type E3, associating two cross-architecture operands with the same value. It will establish dependencies between the numeric constants, identical symbols, and identical string literals of different architectures. For a similar purpose, we define cross-architecture operands type match each as type E4, associating cross-architecture operands with the same fine-grained category. We consider three fine-grained operand types: registers, immediate literals, and memory address pointers. Finally, we define cross-architecture heuristic alignment each as type E5. We establish associations between the token pairs of cross-architecture instruction sequences if their relative positions meet the specific condition. After building the instruction association graph, we expect to refine the semantic representation of instruction tokens with the multi-relational graph schema. Graph neural network has strong graph structure representation abilities. Our instruction association graph connects instruction tokens with distinct edges. To better exploit the multi-type dependencies, we choose RGCN, a GNN variant that can efficiently handle multi-relational graph data. RGCN extends the classic GNN framework with type-specific parameters to model different types of relations separately, and we stack multiple RGCN layers to learn the substructure of different scales within the instruction association graph. The graph-based instruction association module will generate refined instruction token representation sequences. We send the sequence into another BLSTM layer to strengthen the context information, and then employ the max pooling operation to generate the final binary representations. After that, we set up a fusion function to aggregate the final vectors and feed the results into an MLP classifier to predict the similarity score. The fusion function includes the concatenation, element-wise differences, and element-wise product of the two representation vectors, ensuring the MLP classifier can identify the boundary of them and accurately calculate their similarity comparison result. The overall model is optimized by minimizing the cross-entropy loss between the predicted scores and the ground truth labels. We conduct extensive experiments of our proposed approach on 3 datasets. This table shows the information of the datasets. In particular, we construct a dataset with 7 families of IoT malware samples captured by real-world honeypots and built a large-scale cross-architecture reuse function dataset. We first evaluate our approach at the basic block-level dataset and compare it with 2 manually designed baselines and 3 state-of-the-arts. Results are shown in the upper part of this table. From the table, we can mainly draw 3 conclusions. First, the performance of edit distance, char n-gram, and Gemini with SVM classifier is not ideal, which shows the syntax or statistical features cannot handle the significant differences of cross-architecture instruction sets. Second, inner eye and our approach outperform other methods by large margins, which proves that exploiting deep neural networks to automatically extract the features of binary snips is very effective. Third, our approach can achieve the best performance. The improvement is mainly because our graph-based instruction association module can effectively bridge the gap in the representation spaces of cross-architecture instructions. We designed 3 abolition variants to evaluate the core components of our graph-based instruction association module. The lower part of the table presents the results of the abolition experiments. It proves that the mono-architecture and cross-architecture associations all contribute to performance improvement, and separately aggregating neighbors from different types of dependencies can more effectively refine the instruction representations. Then, we evaluate our approach at the function level dataset 2 and compare it with 2 approaches. The first is EAI, which performs best in the basic block level experiments. The second is SAFE, another function-level comparison approach. It also performed instruction pre-training and deployed the BIGRU network to encode instruction sequences. Then it added the self-attention mechanism to generate the importance weights of decimal instructions. This table shows the comparison results. From the table, we can see that our approach has significant advantages than EAI and SAFE. Compared with basic block level, the function level improvement is more prominent. This is because the function level instruction sequences are longer and implement more complex semantic modules, which increases the difficulty of the task. Our instruction association graph will establish more multi-type edges, and the effect of redraining the representation space of binaries from different architectures is more significant. We finally evaluate the practicability of our method in real-world applications. Dataset 3 is constructed from malware captured in the public network by IoT honeypots. We collected ARM and MIPS malware and constructed a large-scale dataset containing over 460,000 function pairs. We also make comparisons with EAI and SAFE. This table shows their performance on dataset 3, along with the offline training and online prediction time. It proves that our approach significantly outperforms EAI and SAFE. However, due to the instruction association graph and the RGCN-based dependencies aggregation, the training and the prediction time of our method are increased. However, the online prediction speed is still acceptable, as inferencing the similarity of a function pair can be completed in 3.72 milliseconds, and we do not need additional time collecting external code corpus and pre-training instruction embeddings. In conclusion, our method can be effectively applied to large-scale real-world binary comparison collections, providing valuable solutions for defending against malware reused and propagated on IoT devices of different architectures. Our major contributions in this paper can be summarized as follows. First, we creatively designed a novel cross-architecture binary similarity comparison approach with multi-relational instruction association graph. It can associate the semantic dependencies of instructions from different perspectives, bridge the gap in the spaces of cross-architecture instruction sets, and significantly improve binary comparison performance. Second, we implement our solution as an end-to-end system and conduct extensive evaluations at basic block level and function level. Results show that our approach significantly outperforms existing learning-based approaches. Third, we further evaluate our approach on a large-scale cross-architecture reuse function dataset constructed from real-world IoT malware. Promising results prove that our approach is valuable for defending against malware spread on IoT devices of different architectures.
Hello everyone, my name is Qian Qiang from Institute of Information Engineering, Chinese Academic Sciences. I'll be presenting my work CEMC, short for Cost-Effective Malware Classification based on Deep Active Learning. Now let's get started. Malware has been a major threat to computer systems for decades. A recent study has reported more than 1,336 million malware samples until July 10th this year, and nearly 300,000 samples are newly discovered every day. Malware classification as a fundamental task has been a huge burden for analysts due to this fast emerging speed. As a result, deep learning, termed as DL methods, have been introduced into this area by many scholars and shown impressive performance. However, labeling samples, which is crucial for DL, is often a cost-sensitive task, since it involves human experts. How to select the most informative samples that can improve the predictive capability of classifiers is an essential question that DL-based methods should focus on. A promising solution is active learning, noted as the AL. A learning protocol where informative samples can be selected for expert annotation. The measure of informativeness can be uncertainty or diversity or both, but related works mostly are based on machine learning methods, especially support vector machine. But due to the implementation of DL in malware classification, it has a great practical significance to develop a framework combining DL and AL, which can jointly learn features and classifiers from informative samples effectively. In particular, we propose an AL-based malware classification framework using a convolutional network called cost-effective malware classification. And this is the framework of CEMC. As we can see, there are experts who are responsible for sample annotation. There are training set for the ith round, which is called the D-labeled I. And the ConvNet-based classifier is fine-tuned based on the training set. The samples of unlabeled pool D unlabeled I are fed into the classifier, and the informative samples X-infer are selected for expert annotation. The training set is expanded with these newly informative samples with labels for the next round. Let's go through the major components of CEMC, and the first is malware visualization. There is an observation that the grayscaled malware samples appear visually similar from identical family, and distinct from different families. So it is reasonable to take grayscaled malware samples as a representation of original features for malware. In our work, binaries of malware are transformed into 224 times 224 grayscale images as the input of classifier. The second is model initialization. We take two kinds of initialization into account here. One is initialization directly with randomly selected labeled samples, D-labeled 0. And the other is a two-stage initialization, including transfer learning from CV area before initialization with D labeled 0. We will discuss the impact of initialization based on these two scenarios later. And the next is model training process, which is the main procedure of CEMC. The classifier is fine-tuned with training set, and samples from unlabeled pool are fed into the classifier. Informative sample set X-infer selected for experts annotation, and after that, training set and unlabeled sample pool are updated correspondingly. The essential step is the algorithm information sample set selection. Let's talk about the detail of this process. Given a malware sample X with label Y, The corresponding outputs of the network P can be calculated as a function of W and Z, while W is the width vector of the last full connection layer, and Z maps X to the output of the network's penultimate layer, which is also the input of the last full connection layer. From the equation illustrated in this slide, we can draw a conclusion that the gradient of W is the scaling of the output of the penultimate layer with specific sample X as the input. That is to say, the prediction Y hat and the output of the penultimate layer Z can be used to estimate the gradient of the parameters induced by samples. For deep learning methods, the network is updated based on the gradient directly. So it is obvious that the gradient of W can be seen as the identifier of the impact for samples. Also, the direction of a gradient vector can be used as a measure of diversity, while the magnitude as uncertainty. This slide shows the detail of a CMC algorithm. For each round, the classifier is trained for epochs. And for each sample from unlabeled pool, the hypothetical label Y hat is computed, also with the gradient Gx. After that, the samples are clustered into Q clusters based on the Gx into Q clusters, and X-info are generated with Q samples nearest to each center of clusters. Now it comes to the experimental setup. The dataset we use is the famous big 2015 with 10,868 training samples from 9 families with official labels. The samples are uniformly split as unlabeled pool and testing set of each family with the same ratio, except the family symbol. We utilize AlexNet as a classifier structure, and transfer learning is used for initialization. For each round, 50 samples are selected for labeling. We also implement several baseline strategies for comparison, which are listed here. Randomly sampling, which randomly selects Q samples from unlabeled pool. Least confidence sampling, which selects top Q samples with the smallest predicted class probability. And the third one is entropy sampling, which selects the top Q samples according to the entropy of the predictive probability distribution. The last one is k-means sampling, which clusters the output of the last linear layer for each unlabeled sample via k-means into Q clusters, and selects the samples nearest to the center of each cluster. This is overall performance compared to baselines. CEMC shows best performance with only 950 labeled samples, which is less than 10% out of the training set after 15 rounds. So it can be concluded that CEMC can achieve best performance compared to other strategies. For more detail, the accuracy of CEMC through 30 rounds compared to the other strategies is depicted as learning curves in this slide. And CEMC performs consistently better than other methods clearly. What's more, there are some interesting observations from this curve. The performance of these 5 methods can be separated into 2 groups in a clear margin. and the gap has no intent to narrow down. The advantage of CEMC compared to LS and ES becomes smaller with the number of labeled samples increasing. Next, for better understanding of CEMC, we also conduct experiments from family perspective, and this is a confusion matrix after 15 rounds for CEMC. CEMC performs best on 7 out of 9 families with little difference for the left 2 families. And the second best strategies are KS and ES, with best performance for 3 out of 9 families. We can draw the conclusion that the advantage of CEMC is stable across different families. Also, we want to stress the effectiveness of CEMC selecting informative samples. We divide the 9 families into 3 categories based on the number of curious samples selected by CEMC compared to random sampling. The first category is named same. The performance of CEMC is better, or at least almost the same compared to other strategies. The next category is called less, and CEMC obtains better performance with less labeled samples. This phenomenon infers that CEMC is able to neglect samples with less information. The last category is more, and CEMC obtains better performance with more labeled samples. The most interesting family in this category is Simba. There are only 25 samples from Simba in the unlabeled pool after initialization. CEMC succeeds to dig all of these 25 samples out of 9,575 candidates, which is really hard. This phenomenon implies that CEMC can fulfill the target of this paper, to select informative samples even though the samples are sparse. Now let's talk about the impact of query numbers selected for labeling each round. This is a accuracy curve for different query number, and a smaller query number shows an advantage over a larger one. We can say that identifying and acquiring more samples does not benefit the classifier consequently. As a result, in order to receive a maximum performance, the query number should be carefully tracked and defined for further implementation. The last experiment reviews the critical effort of high performance initialization. For directly initialization, there is longer startup and smaller performance improvement. This can be explained by the theoretical considerations of all AL-based methods, that the prediction is used to estimate the information that samples can offer, which asks for relatively high accuracy after initialization. So the high performance initialization is critical for CEMC and other AL strategies as well. Let's summarize the conclusion here. First, this paper proposed a malware classification framework named CEMC, which employs a well-designed ConvNet-oriented AL strategy. This strategy can progressively select the most informative samples according to the estimated gradients towards the last linear layer. These layers samples are sent to experts for labeling and integrated into the training set afterward for model fine-tuning. Comprehensive experiments are conducted to analyze the performance of CEMC versus other strategies on the benchmark dataset Big 2015. CEMC shows stable and outstanding performance across all the families compared to other strategies. Also, the contribution and impact of query numbers and initialization are discussed thoroughly. Some useful advice is given for further implementation. That's all. Thank you for your time, and please let me know if you have any questions.